All right, section 6.3, we're going to pick up where the last video you saw left off and talk about theorems of exponents.
I think we need to do definition of exponent.
Definition of exponent first? Okay, no problem. Did I pass it already? There it is. Okay, so we'll start with definition of exponent. Thank you. All right, so for a rational number a and a natural number n, a to the n is a multiplied by itself n times. So multiplication can be thought of as repeated addition, and exponents is actually what happens when you have repeated multiplication. So multiplying a number by itself a bunch of times is actually an exponent. And we have 6 exponential properties that we're going to take a look at, and I'm going to talk about why they work after I show you what they are. I will not ask you on a test or anything like to show me why. The reason I am showing you why in a moment here is because you're going to have that kid someday in that class who's going to say why to something you teach. And so the more exposure you've had to answering some of those why questions, at least lets you know, I've seen this before, now I can go figure it out again, and it's not brand new. Instead of just saying, well, just because that's the way it works. Please don't tell your kids that's a really bad idea, okay? All right, so these are the 6 properties that we're going to start with. We'll see what you remember. If you've had number theory, we do some of these in number theory in chapter 3. If not, that's fine. Does anybody remember what happens when you have a to the m times a to the n?
You add the exponent?
Yes, you do. So this is a to the m plus n. So if you multiply these together and ends up adding exponents, what do you think happens when you divide them? You subtract. So that's the second one, a to the m minus n. Now number 3 looks kind of like number 1. You'd have 2 exponents. There's multiplication going on, because at least it seems like it, because there's these parentheses. But what happens is you're actually taking the a to the m and you're raising it to the power n, not multiplying it by something else with a power of n. So this one gets the exponents multiplied instead of added. So an exponent raised to an exponent is multiplication. 4 and 5 feel very much like a distributive kind of process. So when we have ab to the power of m, it means we're going to have a to the m and b to the m. And then in very like fashion, on number 5, we have a to the m over b to the m. Number 6 is the most interesting. So on number 6, we see a negative exponent showing up. Otherwise, it looks a lot like number 5. So the negative exponent flips the fraction upside down, all right? And other than that, it does the same thing. So I'm going to take this in sort of 2 steps. This is like having b over a now, because it flipped because of the negative, and then you're raising it to the power m. So we end up with b to the m over a to the m. You're all dying to know why they all work, I know. All right, so let me first preface it by telling you that I'm not really giving you real mathematical proofs, but I am showing you an example. Because if your kid asked you, that's what you would do too. You would create an example to show them why it worked, and that would make more sense. So we're going to look at these from an example standpoint. So from an example standpoint, this one is, well, the rule is that these are supposed to be added. So from an example standpoint, we're going to do this example. A to the third times a to the fourth. Okay, so a to the third, by our definition of exponents over here, says that it means I have 3 a's multiplied. And a to the fourth means I have 4 a's multiplied. And if you were to count all those up, how many a's do you have? 7. And how in the world did you get from 3 and 4 to 7? You added, right? You added. So that's the property at work. It's addition. The second one was supposed to be subtraction, m minus n. So the example that we're going to do is a to the 4 over a to the actually a to the 5 over a to the 2, sorry. Okay, so a to the 5th means I've got 5 a's. And a squared means I have 2 a's. Now, it's multiplication across the top and it's multiplication across the bottom, right? So we can scratch them or we can mark them out because we are reducing fractions, right? I'm really dividing both the top and the bottom by a, and I'm doing it twice. And when I do that, what am I left with? 3 a's. And how did I get from 5 and 2 to 3? You had to subtract. That's how you get there. Okay? So far, I have just ruined all the fun that you thought that these were. They looked very magic-y, and now they look very boring. And you're like, well, obviously, right? Obviously. Okay. The next one is supposed to be multiplication, mn. So, another example. We will do a to the 3rd squared. Okay, so a to the 3rd means 3 a's. A. And squaring means to multiply something by itself. So I've now got a and another a. I'm running out of space. How many a's is it? 6. And how do you get from 2 and 3 to 6? You multiply. You multiply. Right. All right, number 4 is this sort of distributive property that we talked about. So we're going to do ab cubed. So cubing means multiplying something by itself 3 times. And back in earlier chapters of the book, we talk about different properties of whole numbers and integers that allow us to commute. That's to turn the objects around. You know, like a times b is b times a, and to regroup things. So we can move things around and we can regroup them more conveniently to have, you know, like all the a's together. I'm running out of space. And then all the b's together. So all the a's together, there's 3 a's, would be a cubed. And all the b's together would be b cubed. Right, and you see that 3 distributing to each of the a and the b individually. Number 5 and number 6 we'll do real quick so that we can head on out. It works the same way for division. In fact, we'll use virtually the same problem, a over b cubed. So it means a over b times a over b times a over b. And if you multiply straight across the top, that's a cubed. Straight across the bottom, it's b cubed. And then the last one, we said that this should be b to the m over a to the m. So what we want to recognize when we're talking about this one, using the example with a -3, is that -3 is really just 3 times -1. So you can break it apart in either order. So I'm going to break it apart as 3 here times -1 here. So in a very concrete way, we have this 3, and then sort of using a property in reverse, I have the -1 on the outside. -1 flips things upside down. So now I have b over a cubed, and then the cubing from problem 5, or property 5, is b cubed now over a cubed. We'll pick up next time with our couple additional properties and then utilizing these. So our goal is to use the properties after I've shown you that they really work, not to continue to re-show them every time.